Welcome to Advanced Embedded Systems. Today we are going to be doing an introduction to Lab 4, which is function generation. Don't forget to do your time logs via the Google spreadsheet that I posted. And today we're going to get into how to build essentially a function generator. We're going to have a function generator that's going to generate this output waveform with a high degree of accuracy and period and frequency, essentially. So we're going to use a lot of what we learned about direct digital synthesis to produce this audio waveform. You may choose any waveform you want as long as it's not piecewise linear. Piecewise linear, if you go to that Wikipedia site, anything that has a lot of straight edges on the waveform, we want something that has curved data, sinusoidal or something else. More variations in the graph, not discrete variations in the graph. Some interesting examples would be sinusoids, the sine C function, exponentially damped sinusoids, or you can actually use waveforms from an actual musical instrument. I just opened up the Wikipedia page on sine C. It's kind of an interesting function. You plug in these values, and I'll show you how to do that using the spreadsheet from lesson 25 towards the end of this lesson. But something like minus sine of x over x, or minus sine pi of x over pi of x, gives you a pretty unique signal. And then you'll put one cycle of that waveform in 1024 bytes of memory in your VRAM, or words of memory. But it is your responsibility to get those samples. You can use things like deriving the waveform with something like Python. I'll show you using the spreadsheet. Otherwise, you can digitize samples using your Lab 3. You can always digitize samples using Lab 3. All right, so once you have that data, then you're going to hardwire it into VRAM using the init statements, which I'll show you that. You can get those an example of that on the handout from lesson 26. This is the lesson handout. But, and again, here it is in the slides. Remember, for this VRAM initialization, it's very similar to what we did, except we're just adding these line for init statements to initialize our 64 rows of memory, or 1024 words, 16 bits of memory. So right now we're changing the read and write width to 16 bits versus 18. Memory address 0 starts on the right, on the top. Memory address 1, that counts to the left to 15. And then the next row is address 16, and it keeps going. I skipped a few rows for brevity, so if you wanted to actually use a regular sine wave, you'd have to generate that yourself. And then it goes all the way to the 64th row, or 63rd row, 0 to 63, and our 1024 is the last. 1023 is the last value. Again, ultimately what we're doing is we're initializing VRAM, and then we're using counter. Again, our address is only 10 bits wide because we only have 1024 values in VRAM. And then we have this sine wave in VRAM, and on every ready edge, we're going to read some value out. We're going to index into that lookup table using 16 bits. We're going to use .6, so 6 bits of fraction, to index into that, and then basically changing the output frequency based upon how fast we index into it. So that's going back to a lot of what we learned on lesson 26 for DTS. All right, so the requirements. You have flexibility to design the waveform generator as you see fit, but you must meet the following requirements. So, update rate of 48 kilohertz, pretty easy. You already have a audio codec that updates at 48 kilohertz, approximately every 21 microseconds. You want to generate at 440 hertz, the lookup table should be incremented by about 1 index value. So if you go back to lesson 26, we'll take a look at that in a second. You also want to be able to make a frequency between 1 and 0.25 hertz change in frequency. So that's a very small amount of increment between the frequency. And you must be able to generate a full amplitude waveform. So if we go back and look at some of those questions, and if you go back to the lesson 26 or lesson 25, zoom or view page source, the answers to those questions were here as well, but ultimately those questions were what phase increment do we need to generate a frequency of 440 hertz? And that was with 1,024 samples and a 48 kilohertz sampling rate. To generate that signal, we needed an index value of 9.387. So our basic requirement of our system is being able to increment to get 440 hertz out of our system. So we'll be incrementing the base rate base phase index will be 9.387. And to be able to make between 1 hertz and 1/4 hertz change in frequency, remember if you look at the smallest change in frequency that we could make with a 10.6 signal or phase was 0.73 hertz. So obviously you're going to have to use 6 bits of fraction. So that's why I post this on here. Tip, most likely you're going to use your slider switches to update that fractional portion, and you only have 8 bits for that, so it'll be a 2.6 on your sliders to make that, to meet the design requirements for the lab. So again, you're going to use these 8 switches and your buttons on this one to do an audio output. There is no HDMI, but you maybe later you might use your UART along with the microblaze if you do the A functionality. So you're going to do a Q2.6 fixed point increment for your phase, and then you're going to have the buttons. We're going to talk about those in a bit. Those are going to be used to increase your amplitude and your and then change your frequency. Required functionality: use the slide switches and push buttons to manipulate the phase angle and the amplitude of the waveform. So phase angle is essentially your frequency, and your amplitude would change the Y value of your axis, your voltage amplitude. Pressing the left button would decrease the frequency by a set amount on the slide switches in a Q2.6, and then the right button should increase the frequency by that set amount. The waveform will be played back through the audio codec interface to the output channel. And you're going to wait for that ready signal to give it a new word of data, 18 bits or 16 bits plus 2 bits of 0 at the end. To achieve B-level functionality, you have to create do achieve required functionality, and then you're going to have the up button increasing amplitude by a set amount on those slide switches. You decide on how much you want to increase, and then the down button will decrease the amplitude. Pressing the center button should toggle between the two different BRAMs. So you're going to implement two different waveforms in BRAM, non-piecewise linear, and then generate those output waveforms. A-level functionality, you'll plug in a microblaze to capture keyboard inputs and to manipulate the amplitude and the frequency to produce a waveform. Basically, the user can enter an integer frequency, and then you calculate what index value you need to produce that waveform, and you will write that value to your phase index and change that output frequency based upon that. But also have keyboard inputs manipulating that instead of buttons. For gate check 1, and that'll be due today, instead of a printed copy, you need to upload an image to Bitbucket by basically the end of today. Diagram drawn in Paint or PowerPoint, you can use what we used in the last previous labs to do a block diagram. But you want to have your top level entity, which is lab 4, and all the borders for each of the components instantiated within that. So you're going to have a data path, a control, probably your audio codec in there, and how all those things are interconnected. All components names must be in the upper left corner, just like in the examples. All signals entering and exiting must have their port name defined just inside the border. And all signals outside must have their width defined, unless it's just 1 bit, as well as labeling the names. At the end of the second lab period, that'll be after spring break, you should have a working test bench. And I have an example in the slides to take a look at so you can kind of get an idea what it's supposed to look like when simulating your design. You're going to have to generate a mock ready signal in place of the ready signal generated by the audio codec wrapper. The audio codec wrapper is not able to generate that ready signal without a lot of extra work. So we're just going to manually do that. When complete, your timing diagram should look like what we have below and must contain at least the clock signal, the ready signal, FSM state, BRAM address, phase increment, BRAM data out, these coefficients if you're planning on aiming for A or B functionality, and then your slide and button values. Your sim should simulate a button press and release and change the phase increment and show that it's incrementing by that new value. And I'll go through this shortly. So if you take a look, this shows the state machine for my system, where it's going through. So let's go into that before I go through an example of how to hook all this up. So make it a little easier, I'm going to show you in my simulation. You'll notice I have my buttons, my slider switches. Slider switches are just set to an arbitrary value of AA. And then I have my buttons. The first button coming in is going to increase my amplitude. And you can see in my states for my FSM, I say increase amplitude. So my amplitude starts out at 3 FFF, and then increases by the value on the slider switches. If you do the math between this value and this value, which I can show you that. So we got in hex, got 4A 9F minus 3FFF. You get A0. Notice I actually took these values on the slider shift and shifted them left by 4, so I put a nibble of 0 on the bottom of that just to make it increase the amplitude just a little bit more. You'll figure out what value works for you to increase the amplitude, but not too much that it overflows the system. And that's all right. So next thing we do, next button is decreases our phase. Notice the initial phase is 259. That is actually in hex 259. That was 601 in decimal, which if you actually divide that 601 divided by 2 to the power of 6, that's a basically 3.3 or 9.387. That was our phase index value. Remember when we did that conversion before? 9.387 times 2 to the power of 6 to convert to that 10.6 format. We got almost 601. So that's where we get that 601 value. 601 in hex is 2.259 hex. So that's our phase index value, our initial phase index value. That should generate a 440 hertz signal. So I have this button that's decrementing my phase, and you can see based upon the slider switches, it will decrement my phase. And if you do the subtraction on that, you can find out how much I decrement by. So 2.59 in hex minus 1AF, we get AA, which is what was on my slider switches. So a 2.6 value I'm subtracting right from the 10.6 value. And I get my new phase index. And then I decrease the amplitude. It decreases it by that amplitude again. And increments phase, and it goes back to 259. So in between there, we're actually reading values on our ready signal. So on ready, we're supposed to get sample. The first sample we get is index 0, which just happens to be memory address 0. You can use these initialization values to start out with your simulation before you actually generate your whole waveform for your initialization, just to test it out and make sure it works. So that index, that first index, it gets that value, and then we'll look for the next ready signal. Notice we're going to get sample, we get the next value, which was 9.387. So if I look in here in my VRAM, I have the first 0, 1, 2, value 3, 4, 5, 6, 7, 8, 9. Notice that ninth value is 870F, which just happens to be that next increment value, which if you remember back from previous lessons for lookup tables, you're going to actually have to take that value and the next value and calculate your offset. to get some linear interpolation in between there. Start out, just use the base value and try to get that output before you try to do the linear interpolation between. So use this base value, and then you're calculating your adjusted output. So ultimately, initially, that was my raw output for this example. This is what I'm going to output. I'm not in the basic example that I gave you. It's not doing any linear interpolation in there. It's just giving you that base value as an output, and then it converts it before it goes out to fit on the screen, or fit within the 18 bits. You're going to have to add 2 bits of 0 on that 16-bit value to extend it to 18 bits for the audio codec. All right. The next value, notice from that value, we reduced our phase index. So for this next value, we had 9.37 plus 1 AF, which we can use our trusty dusty calculator. In hex 259 plus 1 AF gives us 408 hex, and decimal is 1023, and convert that to 23 divided by, get rid of the fractional portion, divided by 2 to the power of 6, we get 15.9, which the value that we read in is 8C, 8A, which is actually value 16. So it got rounded up in the system, and we're basically taking a base address of value 16. Then, so yeah, 408 was our read address. Hexadecimal, and we calculated that out. Next value is going to be indexed by 9 again, so 408 plus 259 is going to give me 661, decimal value 1633, clear 1633, 2 to the power of 6, give me 25. Or you can just look at the upper, just basically erase the lower 16 bits here, and you get that value. So that's 25, index of 25 in here. So you got 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 938C should be that value, 938C, reading that value in. Now, last thing before we end, we're going to talk about how to convert this DDS signal, the DDS spreadsheet, from less than 25 to be 1024 values. So you have your theta value. They're indexing into 3.14 divided by half the values in your lookup table. So if you're going to do 1024, you're probably going to divide by something like 512. And then I would go ahead and I would just create a new tab, copy it, and we'll call it create a copy. OK. Move it over. And then I would call it, rename it, DDS 1024, something like that. Now, these theta values, again, 0 is the first one. The next one is going to take the previous value plus 3.14 divided by, let's say, 512. Would be half of it. And now I'm going to scroll down to 1024. Starts at 1. 1024. It'd be easier to go in this way. 1024. 24. Shift. Gotta use the shift key. Shift, go up. Shift and control. Get those values. And then I'm gonna fill it down. Notice it fills those values in to go the whole distance to 2 pi. And then this is a sine function. Currently, it's going to break your waveforms. You're going to have to reevaluate those. But you can get those values, extend it, and then you got the sine of that value. Come on. Fill all that down. So right now we have a lookup table, 8-bit value. And you can look at it, it's going to truncate the value of 127 times the value in B6, so the sine of that, the real sine value of that, plus 127, it's basically putting it on a scale to 127. You might have to change the scale to something that is more bits, because you notice 127 in decimal is 7 bits, so it's going from 127 all the way up and all the way back down to 0. Right, so it keeps it as a positive waveform. So from 0 to 256. So you can actually change that to something that'll be 16 bits. Just a couple extra zeros or ones. That's going to be 32,767. All right, so you can go along, try to figure that out, and then plug it in so you can actually view the waveforms if you want. Change the data on here. You can reselect the data. If you output those values here, for mine, I'll show you. I went through, took those. That's not the one. Another spreadsheet. So I went through these given values and I converted them. I actually put it on a level 2 to the power of 15, changed the max and min values, and then I got those values right in the middle. You see the middle value where it was 127 or 128. It's now 8,000 hex, which is 32,000 and some change. And then I do a decimal to hex, and I have 4 hex digits. Then I can take those values here and copy them, or you can actually do some concatenation functions where it takes some clever stuff in spreadsheets where you concatenate these in reverse order for 16 words, so 0 to 16, and concatenate them all together into the rows, so then you can just dump them into init 0. Ultimately, I'll let you figure out how to concatenate all those together. You can write a program that'll do it. You can use Excel, you can use Notepad and some clever manipulation. And then on each of the 64 rows, you write the init values from 0, 0 to 3F, and getting all those values in and plugging them into your VHDL code. And that concludes the lesson for today, which is function generator for Lab 4. Again, probably have to, I do have a bonus functionality, I guess I didn't have that on slides. Connect your A-level function generator to your Lab 3 functionality, since you only have one board and you won't be able to utilize other folks' boards. I'm going to have to think about how we're going to do that, but I'll get back to you on that.